My name is Brad Benton. I work at AMD. I work in the research group there. And what I'm hoping to accomplish today is to provide a bit of an overview of 3 new low-level system interconnects, give a bit of a description of them, and also solicit some discussion as to their intersection with the OFA and OFA software. So there are 3 new bus interconnect standards that have been announced in the past year. And people have probably heard something about them. I want to go through and give a bit more detail about each and establish some comparisons. My goal is not to establish any qualitative aspects, pick one or any over the other. It's really just to sort of give a lay of the land of each of these. And consequently, that's why I present them in alphabetical order and try to preserve that. The first one that I have on the list is known as CCIX, which stands for Cache Coherent Interconnect for Accelerators. And there you see the website as well. GENZ, which is largely an HPE initiative, but it's broadened, of course. And then the third one is sort of an evolution of CAPI, which is the coherent accelerator processor interface that IBM has been using with their processor 8s. And they've now sort of taken that out of OpenPower and put it into its own organization and consequently renamed it Open Coherent Accelerator Processor Interface, or OpenCAPI. What is driving a lot of this? There are, of course, a lot of sort of new memory technologies coming on board, as well as the use of GPUs and FPGAs, which really is driving the need for and desire for a tighter coupling between processors and these other accelerator and storage elements, storage class memory, et cetera, et cetera. And really an attempt to streamline a lot of these software stacks where you don't have to do a lot of, at the application level, memory copies into and out of, say, a GPU space or something like that. And of course, a very strong desire to provide open source solutions, open standard solutions, I should say, to these problems. Now, why 3 different standards? There are different groups that have been working to solve somewhat similar problems, but they all have different takes on it. Some overlap, some not. And so that's what we'll cover in the next, in this ongoing set of slides. So each approach has its differences. Now, one thing that I will point out is that a lot of companies have multiple memberships in these consortia. So it's not as if there are 3 separate groups that are composed of 3 complete different membership companies. So a lot of companies are sort of angling their bets or working on ways in which they can integrate actually multiples of these. Now, we've seen some things like this before, and shakeouts often occur or convergences occur. I mean, way back before InfiniBand came as a result of bringing together 2 separate competing standards at the time. And so I think there will also be some sort of drive, expect some sort of drive along that as well. So this is just a list of each organization and the membership companies. Now, looks like a lot of companies up there, but as I mentioned, a lot of companies appear multiple times. AMD, for instance, you will find on all 3 lists. IBM on 2 lists, Mellanox on all 3 lists. So ARM is well represented. So there really is quite a bit of overlap and cross-pollination or that can happen along these things. But I want to drill a little bit further into that, sort of to draw these distinctions. So I have 2 charts here. One shows the membership count for each consortium. And you see they're sort of more or less equally populated. And membership here is also not a strict one-to-one correspondence from each organization. Some have multiple levels of membership, others don't. So it's not, don't take these numbers as hard and fast, but just as an idea of really sort of the level of interest. So on the left, you see, again, sort of an equal distribution. Now on the right, I have stack charts showing what is the composition of the organization in terms of companies that are only involved in that organization or companies that have memberships in one of the other 2. So you'll see almost half of each organization's membership is composed of member companies that are also member of one or two of the others. So, like I said, many companies have dual, and a few even have triple. So now I want to go through sort of giving a high level on each one of these approaches. First, let's talk about CCIX. It's really, if you think of PCIe with sort of the proposed Gen 4 coherency extensions and extended speed mode, it looks a lot like that. And so it has also a lot of similar characteristics and mechanisms to hook things together that PCIe does, where you can have switches, for instance, and so it can be a point-to-point or a switched architecture. And I show initially it's got sort of the bandwidth that's defined as 16 gigatokens, 16 gigabits per second, or 25 gigabits per second. 16 corresponds to the PCIe Gen 4 standard. 25 is, I think, was initially proposed as ESM, extended speed mode, in PCIe Gen 4, and so that's been also adopted for supporting in this. The key aspect that is reflected in its name is hardware cache coherence enabled across the link. So coherence protocol is part and parcel of the CCIX specification. And similarly, I say similarly, in conjunction with that, there's really a strong attempt to be completely independent of the processors that are attached. So it supports multiple processor ISAs over a single interconnect standard. And its goal then, you can use it to extend processor cache coherency to GPUs or to other kinds of accelerators, FPGA-based accelerators, networks, storage adapters, and so forth. And then there are sort of pictures there on the right that show different kinds of configurations that one could put together using CCIX. GENZ is a very extensive and broad approach to treat everything as sort of centralized through memory semantics. And it does this through a split transaction concept by which everything interacts through GENZ through a media controller. The media controller, behind the media controller is the implementation of that. So the interfaces are abstracted in terms of GENZ talking to a memory controller, and then behind that, the implementer can provide the GENZ functionality as needed, whether it's storage class memory, whether it's an accelerator, so forth. Now, it supports both point-to-point and switched, and further up the stack, fabric technology. So it has a much broader reach than CCIX, or in this case, OpenCAPI, in that it extends outside of the rack. In fact, it allows up to 4K number of components of GENZ components on a single subnet and up to 65K subnet. So it's really establishes a broad sort of set of possibilities from within the node, within the rack, across racks, and so forth. Now, I gave some bandwidth numbers. Those are really sort of projected or possible memory bandwidth numbers, but there are a lot of knobs to choose from there, and when I get to a comparison charts that shows that, those will be called out a little bit more directly. Now, it also acknowledges that it is not necessarily going to be the complete fabric, and it has mechanisms to provide gateways, or it's possible to gateway to other networks, such as Ethernet or InfiniBand. But as I mentioned, it really tries to unify data access as memory operations, although the concept is not just load and store memory operations. So underneath the sub-bullets there, I show the kinds of different sorts of operations that it supports. Byte addressable load store, which makes, when you think of memory, that's what I think of. But also supports messaging through puts and gets, and it will also have sort of legacy support for I/O. And so it really is, like I say, a very comprehensive approach to this. And among the use cases, you can view GENZ componentry being able to be the infrastructure for disaggregated memory, disaggregated storage, persistent memory, and as I also mentioned, it really supports long haul as well as short haul. I give on the top there is just sort of a graphic that shows that kind of disaggregation through pooled memory, for instance. And even accelerators could be accessed and dynamically assigned, for instance, to processors as you generate a job. On the lower left, it shows a sort of standard way in which you could take some GENZ components that then talk out next to a broader fabric, or you could have a completely GENZ. On the right there shows a GENZ connection to multiple CPUs, and then they have shared storage, for instance, through storage class memory. OpenCAPI. It is also a mechanism to provide tighter interfaces, but it is much more restrictive, and it certainly does not have switch capabilities. It's also point-to-point, but the points there are really from accelerator to processor or to the CPU and back. So it's not all, it really does not support cross-device connections. And part of this is, reflects the architecture. Initially, CAPI had an architecture in which IBM provided an IP block called PSL, the Power Service Layer, which would then be integrated onto the CAPI-based component. And that PSL would contain such functions as doing the virtual to physical address translations and so forth. Now, in going forward with OpenCAPI, what they've done is push that functionality back on the CPU. And so this is coming out initially with the Power 9 architecture. If you look at the Google Rackspace Xios platform, it's going to be a Power 9 base, and it supports OpenCAPI, for instance. But what happens is the processor manages the conversion of the virtual to physical addresses. The accelerators, adapters, are expected to work strictly with virtual addresses and not put physical addresses on the wire. And IBM's been very strong about that in terms of being able to provide security and isolation and keep everything in terms of being able to deal with physical addresses underneath their control within the power block. There is numbering with CAPI has got a little weird for a while in that the OpenCAPI was going to be labeled 0.7 or 0.8, but now they've sort of cleaned up the numbering, and OpenCAPI 3.0 is what will be coming out with the Power 9 and like the Xeus platform. They also have plans for moving forward with OpenCAPI 4.0. OpenCAPI 3.0 will be using 25 gigabit per second PHYs with by 8 lane aggregation. And what it provides is the accelerators have coherent access to system memory. So the accelerator can go request memory and get it from the system, and it will be the latest, greatest stuff. It doesn't work the other way. So the system isn't going to have, there is not coherence on the accelerators. The accelerators devices are not cache coherent in 3.0. In 4.0, they will be adding support for caching on accelerators. So there are multiple levels among these things, and I'll get into that a little bit later as well in terms of the coherent support. In 4.0, the idea is to also support additional link widths. I think the use cases are pretty obvious and very similar to the others. So this graphic, I try to sort of give an idea of where these things overlap, where they extend out. And so it's really, you see the broad one there, as I've indicated before, GENZ really extends both within the node, within the rack, and extending out. Also, I show here sort of the physical layers. CCIX is based on the PCIe physical layer, but both GENZ and OpenCAPI will be based on 802.3, trying to leverage some of the economies of scale of those PHYs that are already ubiquitous and will be in the Ethernet world and so forth. Now here's the busy chart where sort of tries to pull all this together. So let's just step through this. The CCIX already talked about the physical layers for GENZ, both short and long haul PHYs. OpenCAPI is, CAPI itself was originally over PCIe, but OpenCAPI is over something that was called BlueLink, which is a 25 gigabit per second PHY I think that name was taken. I'm not sure what IBM's latest name for that is, but if you go look on some of the IBM supplied information on Power 9 and OpenCAPI, you will often see blue link on those things, so that's what that is. And that's used for both OpenCAPI and NVLink. So NVLink is also part and parcel of using the same physical layer. In terms of topology, both CCIX and GENZ, point-to-point and switched. In terms of OpenCAPI, I say point-to-point, but it's really accelerator to the processor complex and back. And now this is where the bandwidth gets kind of interesting. For C6, like I say, it's going to be based on 16 gigatransfers, 25 gigatransfers, and then by 16 means 32 to 50 gigabytes per second. GENZ supports broad range of signaling rates, and I put 56 gigatokens per second. That really, they've also announced up to 112, so double that even. And then link widths out the wazoo from 1 to 256. So it's just got all sorts of possibilities and capabilities there. OpenCAPI, pretty standard 25 gigabit per second by 8 links. And that, as I indicated with 4.0, will be moving to additional widths in the future. In terms of mechanicals, C6 supports existing PCIe connectors, mechanicals, things like that. GENZ has mechanisms or has indicated they will support legacy PCIe mechanicals form factors initially, but then will develop new GENZ specific mechanicals and form factors moving forward. The OpenCAPI mechanicals are in definition. There is the Zeus design, and so there is a possible approach that's been promoted there. I don't know of any sort of solidification on that as the only possibility, but that's sort of the first one out of the box. Coherence. C6, full cache coherence between the processors and accelerators built into the protocol. GENZ does not specify, does not provide full cache coherence. However, they provide a lot of the infrastructure needed for that. So they provide coherent mechanisms so that you can issue read exclusive, read shared, write back, invalidate. So they have the mechanisms by which one could build their own coherence protocol on top of that. And OpenCAPI, as I indicated, it's really providing the accelerator coherent access to memory, but full cache coherence on accelerators won't be supported until 4.0. Now, based on some discussions I had at lunch, I'm adding a dynamic column here that you don't see, but that is, when will these things come out? Who's going to come out of the block first? OpenCAPI, as you might suspect, given that it's Zeus already has a design there that implements that. Power 9 will be out later this year. Will be out in 2017. C6 also there are indications that it will be out in 2017 as well. I can't point to any specific products, but if you look at their website, one of the aspects of membership that they say is they're interested in companies becoming members who want to integrate C6 into some sort of product within 2017. GENZ is a longer way out, and I don't know the specifics on when that may come out. Perhaps the next talk with the guys from Dell will be able to provide, which is specifically on GENZ, might be able to provide a little bit more insight into that. But I think that's going to be a longer time firming up. So now I want to discuss some of the implications for the OFA. And I admit I do not have perfect insight into this, and so I also want to solicit interaction and feedback and understanding from OFA members who will be involved in this to get the sort of general view as well. I see C6 as being sort of a straightforward extension of PCIe. It's going to be in the box node system interconnect, preserves existing mechanicals. We already go over that. In terms of OFA visibility, it's not a new transport. I don't see it having a messaging layer or anything like that. I think it's going to be really down at the area of the device driver level, that the providers that provide the hardware and provide the device driver will have newer, more efficient mechanisms to be able to deal with that. Could have sort of secondary effects in terms of what happens with the OFA software in terms of the memory coherence and addressing and whether registration may become more efficient or things like that. So I labeled that as visibility limit. Visibility in my mind meaning, do you have a new transport that you have to support in libfabric? The part I'm less clear on is the implications for storage, for instance, because that has a kernel component. This will be drivers that are in the kernel. There could be a sort of a tighter interaction within the storage side, within the DSDA group, for instance. I'll solicit Paul's opinion later on some of that. Now, I do point out that it provides similar translation services as were defined in PCIe for address translation service and PRI. GENZ defines a lot of new stuff. We'll integrate with existing stuff as part of the plan. The exposure to OFA, this I do see having sort of the much more involvement in terms of OFA software, because it does provide a messaging layer. And if you look on the far right picture there, you will see GENZ user library, GENZ provider fitting into libfabric. You see a GENZ user library, so it also shows sort of two ways to access that. One is through presumably direct new set of interfaces that GENZ user library provides that MPI middleware or SHMEM middleware might take advantage of, but also to be able to be effectively used within the existing mechanisms that are provided by the Open libfabric framework. Then it will, they intend to supply GENZ provider components that will fit into the libfabric framework, and that'll then open up their exposure or use to a lot of existing software. And just in terms of their other aspects, not only does it support messaging and memory accesses, but also will also support block I/O. So I think this will also have sort of stronger interaction in terms of NVMe F, NVMe, SCM, those sorts of things that will definitely have kernel components that will be able to get to those. OFA and OpenCAPI. OpenCAPI, as I said, is integrated in Power 9. It supports virtual address to physical translation services, aggregation, possible aggregation of system accelerator and system memory. I sort of put this in the same category of C6. I'm not sure it's going to have strong visibility at the transport layers or other aspects within the OpenFabrics software. Now, are there paths to convergence? Are there paths to integration of one or more of these within the same system? I think the vendors and integrators are anxious for clarity. I think that's one of the reasons why you're seeing a lot of multiple memberships, and people are sort of riding 3 horses now. Maybe they only want to ride 2, maybe 1. I will point out there are some indications that activity is going along those lines from the CCIX website. It clearly calls out the possibility of integrating C6, transferring over to GENZ systems. You can read the quote there, but it certainly sets up the framework in which both can coexist. OpenCAPI has a similar sort of notion that they can also bridge. I think what you will see initially as things roll out in the near term to expect people to play with this, to take sort of an approach to something that it doesn't go strictly initially to ASICs, but use some FPGA-based bridging for interconnect transitions, and we'll see how things sort of fall out in the future. Thank you. And there's another opinion, apparently. So what I'd like to do now is open it up for questions. We have about 5 minutes left. Thoughts, discussion. Jason, please.
So could you talk a little bit more about this? I got the impression that OpenCAPI's use of virtual addresses is unique. Is C6 not able to do that as well, or?
C6 provides translation services, right? So you can, an adapter could have virtual addresses, but then when you want to put something on the wire, you still put physical addresses on the wire.
I see. Because to me, you know, looking at your slides, it's sort of suggested the impact to our community. The use of virtual addresses at like the PCI level or at the NIC interface level is huge, right? The talk that Christoph gave earlier about kernel problems, I mean, it solves our pinning problems. It solves the problems the MPI have using these things. It's a big improvement from
I agree.
a software design perspective.
Yeah. And I agree, and that's the part when I say OFA visibility limited, I was sort of keeping that at the middleware or application level, but certainly at the driver level, being able to have a coherent memory space, being able to...
Well, it's not just a driver. In user space, I get to talk to my NIC, and
that's
it can
true.
DMA into me, and I can do whatever I want, and it all just works,
Yeah.
right? That's the promise anyway. We'll
Yep.
see.
Ted.
You know, I think we're all familiar with the traditional kinds of things you could, connect on, GPUs, whatever. Do you see any new class of device that might be enabled by these kinds of things?
I think storage is going to be very interesting in different kinds of storage memories and things like PIM, processing in memory, where you actually have processors with some that may do some special function, whether it's encryption or compression or things like that. But I think the memory space, because it's distance now, now that storage, like storage is in persistent memory, is being able to approach the speeds of DDR or something like that. I think that's where there's going to be a lot of innovation. And of course, FPGA stuff is, I mean, if you look at some of the stuff like Project Catapult at Microsoft and all like that, the use of FPGAs to do special function stuff is also increasing quite a bit. And I'd like to solicit Paul's opinions on the intersection with OFA storage, kernel.
So you're asking for a knee-jerk reaction, that's what you're going to get.
That's great.
I measure the applicability of technologies like this to work going on in the OFA, in particular OFIWIG, which I think is to what you're referring,
Yes.
as being to the extent to which it looks like a switched fabric. So we're interested in switch fabrics. We don't do much with internal interconnects or nothing with internal interconnects. So just based on your extremely good sketch, thank you very much. This is a very helpful session for me. Feels to me like Gen Z is the one that we would be thinking about here. Here's my question for you. Are there features and functions built into Gen Z, or is the Gen Z community thinking about special features, sort of related to the question that was just asked, specifically targeted at fabric-attached persistent memory, or is it just, we hope it works?
Oh, no, I think they definitely are. If the Gen Z spec is extensive, the goals are broad, and the coverage that they want is, again, deep and broad. So yes, they're definitely looking at persistent memory, different classes of storage, and like I say, particularly in the area of, you think in terms of aggregation and access across the cluster, to have virtual addresses that span these large areas and multiple, what we think of as nodes, being able to get to those.
Are they thinking about transactions over Gen Z as being, sort of memory-based, or are they still thought of as I/O operations in a get-put kind of a style?
There are both. So they provide messaging, gets and puts can support up to, I think, 4 gigabyte transfers. They support unreliable and reliable services. So I think they have a very broad plans.
The reason I asked the persistent memory question, I mean, obviously that we would like to be able to connect persistent memory using something like that, but the API that's exposed through libfabric, for example, if it doesn't already, it's expected to include features to support remote persistent memory, things like cache flushing and synchronization activities, things like that. And we always assume that, well, if the provider doesn't do that, he has to find a way to make that happen. And to the extent that the provider already has capabilities or features built in that make that easier, then things go much smoother, which the obvious statement, that's why I asked that.
So thank you very much.